Welcome to our Advanced DSA series. Today, we're diving into dynamic programming, a powerful technique for solving complex problems efficiently. Whether you're preparing for coding interviews or tackling challenging problems, understanding DP is a game changer. Dynamic programming, or DP, is a method for solving problems by breaking them down into simpler overlapping subproblems. The key idea is to store the results of these subproblems to avoid redundant calculations, making the solution more efficient. Overlapping subproblems means that the problem can be broken down into subproblems, which are reused multiple times. For example, calculating Fibonacci numbers using DP allows us to store previously computed values instead of recalculating them. In this C++ code, the DP array stores the Fibonacci numbers as we calculate them, so we only compute each number once. Optimal substructure means that the optimal solution to a problem can be constructed from optimal solutions to its subproblems. For instance, in the knapsack problem, the best solution for a given capacity can be built by considering whether to include an item or not. In this 0-1 knapsack problem, dp I(W) represents the maximum value that can be obtained with items and capacity W. The decision to include or exclude an item builds the optimal solution. There are two main approaches to DP: top-down and bottom-up. Top-down is also known as memoization, where we solve the problem recursively and store the results. Bottom-up is the iterative approach, where we build the solution from the base cases up. In this top-down approach, we use an array memo to store the results of subproblems, avoiding redundant calculations. In bottom-up DP, we start with the smallest subproblems and iteratively build up to the final solution. Dynamic programming is used in various real-world applications, including financial modeling, bioinformatics, and AI. Problems like shortest path, longest common subsequence, and edit distance are classic examples where DP shines. Let's take a look at some more DP problems that you can solve to strengthen your understanding. Firstly, let's look at the problem description. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones, usually starting with 0 and 1. The sequence goes 0, 1, 1, 2, 3, 5, 8, 13, and so on. Dynamic programming approach that we will follow is to store the results of each Fibonacci number as we calculate it, so we don't have to recompute the same value multiple times. In this C++ code, the array DP stores the Fibonacci numbers as they are computed. DP I is the ith Fibonacci number, and it is calculated as the sum of DP I1 and DP I2. 0-1 knapsack problem description. Given a set of items, each with a weight and a value, determine the maximum value you can obtain with a given weight limit for the knapsack. You can either take an item or leave it, hence 0-1. Dynamic programming approach to be followed is that we use a 2D DP table where DP I(W) represents the maximum value that can be achieved with the first items and a knapsack capacity of W. In this C++ code, DP I(W) considers whether to include the ith item or not. The goal is to maximize the value within the weight limit. Longest common subsequence, LCS. Problem description. Given two strings, find the length of the longest subsequence that appears in both strings. A subsequence is a sequence derived by deleting some or no elements from a string without changing the order of the remaining elements. Dynamic programming approach. We use a 2D DP table where DP I(J) represents the length of the LCS of the first I characters of one string and the first J characters of the other. In this C++ code, DP j is the length of the LCS up to the ith character of x and the jth character of y. If the characters match, we add 1 to the LCS of the previous characters. If not, we take the maximum LCS possible by either excluding the current character of x or y. Edit distance, Levenshtein distance. Problem description. Given two strings, find the minimum number of operations, insertions, deletions, or substitutions required to convert one string into the other. Dynamic programming approach. We use a 2D DP table where dp ij represents the minimum edit distance between the first I characters of one string and the first j characters of the other. In this C++ code, dp ij considers three operations: inserting a character, removing a character, or replacing a character. The minimum of these operations, plus 1 if a replacement is needed, gives the edit distance. Matrix chain multiplication. Problem description. Given a sequence of matrices, find the most efficient way to multiply them together. The problem is to determine the order of multiplication that minimizes the number of scalar multiplications. Dynamic programming approach. We use a 2D DP table where dp ij represents the minimum number of scalar multiplications needed to multiply matrices from index I to j. In this C++ code, dp ij calculates the minimum cost of multiplying matrices from index I to j by trying all possible positions k to split the product. The goal is to minimize the number of scalar multiplications. To wrap up, dynamic programming is a versatile technique that helps solve complex problems by breaking them down into simpler subproblems. Remember the key concepts of overlapping subproblems and optimal substructure, and practice both the top-down and bottom-up approaches. If you enjoyed this deep dive, make sure to like, share, and subscribe for more DSA content. Got any questions? Drop them in the comments below, and let's keep learning together.